SegFly, a 2D-3D-2D paradigm for aerial RGB thermal semantic segmentation at scale. In this work, we present a geometry-driven framework for constructing large-scale RGB thermal semantic segmentation datasets from off-the-shelf uncrewed aerial vehicles, also called UAVs. Our central objective is to transform a small set of manually annotated RGB images into dense semantic labels for thousands of RGB frames and thermal frames, while maintaining high annotation accuracy that enables the training of state-of-the-art segmentation models. The key idea is a scalable geometry-driven 2D-3D-2D paradigm. The pipeline operates on high-overlap geo-referenced RGB thermal imagery captured by off-the-shelf UAVs. From all RGB frames, we obtain a metric 3D point cloud and accurate 2D to 3D correspondences. We then manually annotate less than 3% of the RGB images chosen so that they collectively see more than 99% of the reconstructed points. These labels are lifted into 3D to obtain a semantic point cloud. In the 3D to 2D stage, we present a 4-step point-based renderer that produces dense pseudo-labels for the remaining 97% of RGB frames and 100% of thermal frames, achieving annotation accuracies of 91% and 88% respectively. Crucially, this does not require any manual 2D refinement, so once a scene is reconstructed, labels can be generated at scale with essentially zero extra human effort. A second component of scalability is RGB thermal image registration. Instead of using custom hardware rigs, we reconstruct thermal images into a second point cloud that is aligned with the semantic point cloud. This way, we can synthesize registered RGB views via thermal lens distortion transfer, achieving about 87% semantic level registration accuracy. Since all registration is handled in software, we can use off-the-shelf UAVs instead of custom sensor rigs and still obtain precise pixel-level alignment. Building on this pipeline, we introduced the SegFly benchmark, comprising over 20,000 high-resolution RGB images and more than 15,000 geometrically aligned RGB thermal pairs across 9 scenes, 3 altitudes, and multiple seasons. Remarkably, all of this is derived from manual labels on only about 3% of the RGB data, and no manual labeling on thermal data at all. We also introduce Firefly, a simple yet effective baseline for RGB and thermal semantic segmentation. Firefly combines a frozen Dino v3 encoder with a lightweight MLP head for RGB segmentation, and it uses parameter-efficient rain adapters to map thermal features into the RGB feature space. Training proceeds in 3 stages: standalone RGB training, RGB thermal domain adaptation, and thermal fine-tuning. This stage design keeps most parameters frozen, making Firefly well-suited for scalable, cross-modal training on large RGBT datasets. On SegFly RGB, Firefly and established architectures such as UperNet and SegFormer show a clear improvement when trained on the full pseudo-label set rather than on manual annotations alone. Notably, Firefly achieves the best performance across both modalities. These results demonstrate that our cross-modal adaptation approach, combined with large-scale supervision, is effective, and that the automatically generated labels are sufficiently robust to train competitive models. Finally, we evaluate vision foundation models. Fine-tuning CatSeg on SegFly RGB and AnyThermal on SegFly RGBT yields large improvements over their zero-shot performance. In conclusion, SegFly demonstrates how our geometry-driven 2D-3D-2D framework can convert a limited set of manually annotated RGB images from off-the-shelf UAV data into large-scale, well-aligned RGB and RGB thermal labels. This approach substantially improves the scalability of multimodal semantic segmentation and facilitates further research in aerial scene understanding.